Hello everyone, and welcome to this Node Analysis Sandbox. This video is a quick review of node analysis, followed by some practice problems with solutions. So please do follow along, pause and skip ahead as needed, and I hope you find this helpful. So let's go ahead and get started. Here's the goals of this video. First, we will briefly review the steps of node analysis. We will also have some quick practice to help go through the smaller parts of each step. We'll also talk about how to recognize and solve special cases of node analysis, including supernodes and when we have voltage sources between a node and the ground and with dependent sources. And finally, our goal is to really help everyone get comfortable with node analysis by doing examples of increasing difficulty. Please remember that the best way to improve at solving circuits problems is to practice solving problems yourself. And this is absolutely the case with node analysis as well. So please do consider pausing the video and trying each problem on your own before checking the solution. It is my hope that after you've reviewed this video, you'll be a lot more comfortable with node analysis, and practicing the examples in this video should help make the procedure much easier. So let's go ahead and get started. Feel free to skip ahead or pause the video as needed as we go through these topics. So first, what is node analysis? Node analysis might sound scary, but it's really just a clever way of applying Kirchhoff's laws and Ohm's law. In particular, we use Kirchhoff's current law and Ohm's law to write systems of equations in terms of voltage and resistance. And once we have those equations, we can solve for the voltage at every node of a circuit. And this might sound really simple and not that exciting, but it turns out that a lot of software tools like PSpice, LTSpice, they actually use node analysis to solve for unknowns in circuits. So this is a really powerful tool, not just for introductory circuits class, but also for software as well. So how do we actually do node analysis? For a full explanation, I encourage you to check out Lecture 4 of our circuits videos, but here is the short explanation. So again, full explanation is in Lecture 4. So the first step of node analysis is to identify all the nodes. These are the interconnections between a circuit's components. Next, we choose a reference node. And typically we want the reference node to be the node that's connected to the most things, and we assign the reference node the voltage of 0 volts. Basically, we pick who's going to be our ground. Once we've chosen our reference node, we apply Kirchhoff's current law to each node other than the reference node. And this allows us to get equations in terms of currents. You may need to assume current directions and draw in some arrows if currents are not already given. The fourth step is to rewrite the Kirchhoff's current law equations in terms of node voltages. And so the equations that we need to solve are called node equations. Finally, the last step is to solve the resulting system of linear equations, and we will end up with the voltages at each node of the circuit. Sometimes we might need to solve just one or two equations, but if you have a lot of nodes, you might need to solve a bunch of equations. So it's a good idea to use a system of equation solver if available, if you have a lot of equations to solve. All right, so for the next part of the video, we'll briefly practice a few steps of node analysis, including how to identify nodes, how to apply Kirchhoff's current law, how to rewrite the Kirchhoff's current law equations, and errors to avoid. And so if a lot of this stuff is familiar to you, you can feel free to skip ahead to the actual examples, but I think for completion's sake, it's good to practice these steps, and especially if you're new to circuits or you're uncomfortable, practicing these smaller steps will make the node analysis process much quicker and easier. So please feel free to go through these quick practices first as needed, and then after we finish the quick practice, we will cover special cases and then end with our practice problems. So feel free to jump ahead and pause as needed. Okay, so first, what is a node? We talk about node analysis, and our first step is to identify all the nodes in our circuit. A node is the area in a circuit between components. And this might seem kind of dumb and boring. Why is this so special? The reason this is important is because within a given node, the voltage is the same throughout. And the voltage value of a given node is called its node voltage. And if we know the voltage at various places in our circuit, we can use that voltage to help solve for current or resistance or other unknowns. So being able to know the voltage at different points in our circuit is really powerful. One other caution to point out when looking for nodes in a circuit is that nodes are not necessarily a point. It can be a larger area connected by wire, and remember that a plain wire is assumed to be a short with zero voltage. So if you have 2 points that are connected by a plain wire, those points will have the same voltage between them. And so a node can also include areas of wire. So be aware of that as you identify your nodes. Let's go ahead and practice identifying some nodes real quick, just to make sure everyone is comfortable with this. So here we go, quick practice 1. Let's try identifying the nodes in these circuits. Remember that the nodes are the interconnections between components. So in this first example, we have a node here. I'll just call it node 1. And just kind of working my way around the circuit, I've got a second node here, a third node in the top right. And notice the bottom of the circuit, this whole area is connected by wire. So this whole area is sitting at the same voltage. The bottom of the circuit is my node 4. Another example, this second circuit here. Let's go ahead and work our way from top to bottom, left to right. Our first node is actually this whole area in the top left corner. Because notice this whole area is connected by wire. So this whole area is sitting at the same voltage. Similarly, the whole area on the top right and this area in the middle, these are all sitting. Voltage within these areas will be some fixed value. And then finally at the bottom, we have a fourth node. All right, let's try 2 more quick ones before we move on. So this circuit on the left, we see that we actually have a big node right here. Remember, a node is not necessarily just a point. The whole area of node 1 could be sitting at some set voltage value. And we have a node over here. This is node number 2. And then we have another node on the bottom. And finally, our last example. This circuit has a big node on the top. So this whole area is sitting at a common voltage. We've got some node over here between the 2 resistors and source, another node here, and then another big node on the bottom. So hopefully by now you're very comfortable identifying the nodes in the circuit. And again, very simple, but very important because this is the first step of node analysis. All right, let's go ahead and look at one other quick example. So the next step of node analysis, after we've identified the nodes, is to apply Kirchhoff's current law to each node. And you'll remember Kirchhoff's current law says that the algebraic sum of the currents entering and leaving a node must be 0. And if you check out our lecture 4, you'll see that I like to use what's called the bank account convention. The bank account convention I use is kind of like money in or out of your bank account. If you have money coming into your bank account, it has a positive sign. It's being added to your balance. Similarly, current entering a node can be given a positive sign. That's our bank account convention. So if we have current coming into our node, we give that a positive sign. And current exiting our node, oops, this is a typo here. Current exiting our node should be negative. So for example, if I have this circuit shown, if I look at node 1, we see we have current IS entering, I have current I1 leaving, and I have current I2 entering node 1. Therefore, my Kirchhoff's current law equation will be plus IS, since IS is entering. I1 is leaving node 1, so minus I1, then plus I2, since I2 is entering, and we get that. All right, and similarly, if we look at the ground node of our circuit, that's the area down at the bottom, notice relative to the ground, IS is leaving. So if we were to write a Kirchhoff's current law equation for the ground node of our circuit, we would have minus IS. I1 is coming in, so we'd have plus I1. And then we would have, in this case, I2 is leaving our ground and flowing upward, so it would be minus I2 equals 0. So notice, if we applied Kirchhoff's current law at the ground, we would get a slightly different equation. But you need to keep the currents consistent throughout the circuit. So notice we have IS flowing upward throughout the entire circuit. We can't change our mind and have IS flow downward into the ground. We have to keep these arrows consistent for our whole circuit. All right, the next step of node analysis, you'll remember, is once we have that Kirchhoff's current law equation, we need to write our currents in terms of voltages and resistances. And this can be sometimes a little tricky if you're not careful, so please be careful of a few small possible mistakes. So one thing to keep in mind is when current is flowing, we assume current flows from higher voltage to lower voltage, just like how water flows from higher pressure to lower pressure. And so we want to make sure that we keep that assumption consistent when we are writing our equations. And this becomes important when we are subtracting voltages to find our currents. And you want to make sure you are careful to subtract voltages in the correct order. What we mean by this is we assume that current is starting at the higher voltage and ending at the lower voltage when we draw an arrow. So that means if you are subtracting one voltage from another, your positive current is produced when we subtract the lower voltage from the higher one. So you should subtract the voltage where your arrow ends from the voltage where your arrow starts. Sometimes students accidentally get those reversed, and it will cause some errors. So be careful of that. Here's a couple quick examples. Let's take a look at current I1 in this circuit shown. We know that our current I1 is flowing from our node voltage V1 down to the ground, which is sitting at 0 volts. And so by Ohm's law, we know that our current I1 must be equal to the voltage change, or delta V, divided by R. Basically, the voltage difference across these 2 points divided by the resistance R1. And so in this case, we know that since we are starting at voltage V1, that is assumed to be the higher voltage, because we are assuming our current is flowing from V1 down to the ground. Therefore, we need to subtract V1 minus 0 divided by R1 in order to correctly calculate our current I1 in the downward direction. So as noted here, you'll see that I1 should be written as V1 minus 0 volts divided by R1 because we assume current was flowing from V1 to the ground. Since we drew our arrow pointing downward, we inherently assume that V1 is our higher voltage. And be careful here, because as we mentioned, we cannot say that I1 is equal to 0 minus V1 over R1, because that would be assuming our current is flowing upwards. It's just not how we drew it, and you would end up producing a sign error. One other example, we can consider node 2 in this circuit, and we can see that node 2 is sitting at 2 volts of voltage. And so by Ohm's law, the voltage difference between node 2 and V1 would be given by 2 volts minus V1. So we'd say I2 would be, in this case, equal to our change in voltage over R2, which would have to be our higher voltage of 2 volts minus V1 over R2. And that's exactly what we wrote here. We assume current is flowing from node 2 into voltage V1, so therefore we're inherently assuming that node 2 is at the higher voltage, therefore we subtract 2 volts minus V1 over R2 to get I2. So be careful, once again, if we said I2 was V1 minus 2 volts, that would have been assuming the current was flowing the other way, which is not what we want. So just to summarize, make sure you subtract the voltages in the correct order when you are writing currents in terms of voltage and resistance. Be careful. If you subtract in the wrong order, then you might produce a sign error and cause some problems later on. All right, one last question that I commonly get from students is what to do if the current arrows are not given. Because we don't always get circuits problems where people have drawn in the known current, or sometimes you just don't know which way the current is flowing. And that's okay. So it turns out if the current arrows are not given, you just have to assume a direction. You have to assume a direction because you need to be able to apply Kirchhoff's current law. And here's the thing, you're not always going to know which way the current is flowing, and that's okay. You don't need to necessarily guess correct. Any assumed direction is okay as long as you stay consistent throughout the circuit and as long as you correctly apply Kirchhoff's current law and Ohm's law later on. As noted here, as long as you apply the laws correctly, you will end up with mathematically the correct answer for your node voltage. What will happen is if you happen to guess that one of your currents was flowing in the wrong way, you'll calculate a negative value for the current. So if you're doing these calculations and you end up calculating that one of your assumed currents was negative, that just means that the actual current flow is in the opposite direction as the direction you assumed. However, the node voltage values are the things we're actually trying to solve for, and your voltages will be correct. So please keep that in mind. This is why it's always a great practice to draw pictures, draw arrows on your circuit, and make sure you clearly assume which direction your currents are going so that you apply Kirchhoff's current law correctly. All right, let's go ahead and move on to our next topic, which is special cases of node analysis. We'll briefly review these 3 special cases, and then we will move on to actually solving some practice problems. Here are the 3 cases we want to watch out for. First, when we have a voltage source between a node and the ground, or a reference voltage. Second case is when we have a voltage source between two nodes. And our last case is when we have node analysis when there is a dependent source in the circuit. Let's go through these one by one. First is our special case where we have the voltage source between a node and the ground. So if we have a voltage source, could be independent or dependent source, if we have a voltage source between a node and the ground, like here, notice we have a ground here, and then up top we have this node B. You'll notice that since ground is 0 volts, and node B is, in this case, 2 volts higher, the node's value will be exactly equal to the voltage source's value. So for example, in this case, once again, since we have a ground and then a 2-volt source and then our voltage at node B, we see that the voltage at node B has to be 2 volts because we know the ground is 0 volts, and if we walk up our 2-volt source, we'll gain 2 volts of voltage. Node B has to be sitting at 2 volts. So this is the easiest special case because it gives us free information. Our next special case is when we have a voltage source between two nodes. This is a special case where you actually want to create a larger node called a supernode. So in this case, as noted here, we define the supernode to be this whole area. So it's basically the two nodes plus the voltage source between them. And here's the trick. When you have a supernode, you should be happy because it tells you immediately two things that you need to do. First, we can apply Kirchhoff's current law to a supernode in the same way that we do for a regular node. So notice in this case, we can treat this supernode as one larger node, and by Kirchhoff's current law, we can write the equation plus IS minus I1 minus I2 equals 0. And then similarly, the supernode gives us a second equation. Notice how the supernode also gives us a free equation relating our two node voltages. So in this case, we have our voltage VA, and we had our voltage source V1, and then we have our voltage VB. In this particular example, we see that the VA is V1 volts larger than VB, since VA is sitting at the positive end of our voltage source. Therefore, we can say that VA minus V1 must equal VB. So we get this second equation here. And typically, if we have this second equation along with an equation from Kirchhoff's current law, we will have enough information to solve our circuit. So supernodes might seem a little scary at first, but if you just apply Kirchhoff's current law to the supernode and use that other equation you get relating our two node voltages, you'll find that supernodes are actually nice because they give us free information and a hint about how to solve our problem. We'll do some examples of supernodes later in the video, so definitely check those out if you'd like more practice. All right, so our last special case is when we're trying to do node analysis in a circuit that has a dependent source. And when a circuit contains a dependent source, you should be happy because this gives you free information and a big hint. Basically, what you need to do is relate the dependent source to your node voltages, and then do node analysis as normal. For example, in the circuit shown here, we can actually relate our dependent source, this 8IA. We see it depends on current IA. And if we look over here, we see that current IA can be related to our node voltages V3 and V1. So we can write this extra equation to help us solve our circuit. In this particular case, we see that this example circuit's dependent source also forms a supernode. And so in this case, we could use Kirchhoff's current law on our supernode in order to solve. So it's possible to have a dependent voltage source also create supernodes in our circuit and have two special cases. But that goes ahead and sums up our special cases. Let's now go ahead and begin our sandbox. So please do follow along with our example problems, and we'll get some more practice with all of these special cases. All right, so the rest of this video contains example problems with solutions. And the first problems are easier, and the problems towards the end are more challenging, similar to ones that I've given on exams. So I highly recommend that you pause the video and try each example first on your own. And then you can compare your work with my solution. I realize node analysis can be intimidating at first, and I tell students that the more you practice, the easier it gets. This really is one of the most important tools that we will use in circuits class, and we will use it all semester long. So please make sure you invest the time to learn node analysis well, and definitely feel free to reach out if you have questions on this. So without further ado, let's go through the sandbox problems one by one, and feel free to pause or skip ahead as needed in order to practice these problems on your own. All right, our first example is a very simple example. We want to use node analysis to find voltage across our 6 ohm resistor. And you might be thinking, oh, come on, Professor Erickson, I don't need to use node analysis for this circuit. I could just solve this circuit with Ohm's law, or voltage division, or Kirchhoff's voltage law. And yes, you could, but our purpose here is to practice node analysis. So let's try solving this circuit using node analysis. Just a simple example to help us practice the steps. All right, so let's go ahead and get started. Our first step is to identify all our nodes. And in this case, we have a node at our 10 volt source. I'll just call it V1. We have a second node right above our 6 ohm resistor. Then we have a third node, I'll just call it V3 for now, at the bottom of our circuit. And then our next step is to choose a reference node. So when choosing a reference node, you want to make your life easier, because this is the node that you can set to 0 volts. In our case, I'm going to let our V3, our bottommost node, be 0. And the reason for this makes it convenient for us because we're trying to find voltage between V2 and V3 across that 6 ohm resistor. So having V3 be 0 makes our life easier. Our next step is to apply Kirchhoff's current law to the nodes. And in this case, I want to apply Kirchhoff's current law to my node V2 because I want to get some value for V2. Whatever value V2 is, that will be equal to the voltage across my 6 ohm resistor because I know V3 is 0 volts. So in this case, let's go ahead and write a Kirchhoff's current law equation for V2. So to do that, we need to assume some currents. I'm going to go ahead and assume I have two currents, I1 and I2. So let's say I1 is entering V2 and I2 is flowing from V2 downward. And you might say, yeah, Professor Erickson, those two currents have to be equal. Yes, but bear with me as we're just trying node analysis here. So we can go ahead and say, since I1 is entering, we have plus I1, I2 is leaving, minus I2, By Kirchhoff's current law, those two must satisfy this relation. Our next step is to rewrite our Kirchhoff's current law equation in terms of voltages. So we want to rewrite in terms of our node voltages and resistances. So in this case, let's go ahead and look at how we would find our current I1. Initially, I1 is sitting at 10 volts, and we flow into V2, and we pass through a 3 ohm resistor. So to find I1, we know that essentially we have something like this. So by Ohm's law, we can say that I1 must be equal to 10 volts minus V2 divided by 3 ohms, because the current I1 by Ohm's law is equal to the voltage pushing the current through divided by our resistance. Similarly, for our current I2, in this case, current I2 is the current flowing from our voltage V2 down to the ground at 0 volts. So once again, our I2 is going to be given by the voltage pushing that current through our 6 ohm resistor divided by our resistance. So we get I2 must be V2 volts minus 0, because we have V2 volts up top, 0 volts on the other side, and we divide by 6 ohms. So that's just V2 over 6. All right, so we have I1 and I2, so finally we can substitute back to get. We'll determine, in this case, we have I1 is 10 volts minus V2 over 3 minus V2 over 6 equals 0. So our last step is to solve for V2. And in this case, if we go ahead and take that equation we had and multiply both sides by 6, you would see that we'd end up with 20 volts minus 2V2 minus V2 equals 0. So we would end up here with minus 3V2 is equal to negative 20, or V2 is equal to 20 thirds. So you can see that while node analysis might not be the fastest approach for this very simple circuit, it does indeed give us the correct answer. And had you gone back and tried using Ohm's law or voltage division, you would get the same result. So in this case, the voltage across our 6 ohm resistor is equal to 20 thirds volts. Okay, let's continue on with example 2. Example 2 asks us to identify the nodes in the circuit below, and then we'll use node analysis to find the voltage at each node. We're also specifically told here to let the bottom node be our ground node. Sometimes questions will actually have the ground node given, so here we'll assume our ground node is indeed this bottom node. Okay, let's go ahead and get started. So our first step is to identify the nodes, so let's do that. And I'm going to go ahead and label them. We'll call this first node V1. Then we have this larger node here on the top right. I'll call that V2. And then on the bottom of my circuit, we have the bottom node V3. That one we've already been told is our ground node. So we've been told to assume that's our reference. And notice we also have a special case here. Notice that V1 must be equal to 10 volts. And that's because we have the 10 volt voltage source between the node and the ground. So remember, that's one of our special cases. So if we have a voltage source between a node and the ground, this node V1 must be equal to the 10-volt source because it's 0 volts on the other side. Okay, so we know V1 must be equal to 10 volts, and we know that V3 must be 0 volts because it's our ground. And so that means we need to find V2. So let's go ahead and do node analysis to find V2. All right, so our first step was identifying nodes. That's done. Our next step is to apply Kirchhoff's current law. So let's go ahead and assume some currents. Notice that our currents were not given to us here, so we're just going to go ahead and draw arrows and assume some current directions. Remember, you do not need to try to guess correct. The important thing is to be consistent. So draw in the arrows, and then you can go from there with applying Kirchhoff's current law. As long as you apply Kirchhoff's current law correctly, it doesn't matter which direction you assume for each current. Okay, so I'm going to go ahead and assume my currents are like this. I have I1 flowing from my 10-volt source to the right, and then I have I2, I3, and I4 all flowing downward through the 6 ohm, 12 ohm, and 4/3 amp components, respectively. And so we go ahead and assume those. And our next step is to write the Kirchhoff's current law equation. And in this case, this is at the node 2 with voltage V2. So in this case, I1 is entering. So we have plus I1. Everybody else is leaving node V2. So all the rest of my currents are leaving. They get negative signs. And by Kirchhoff's current law, we know that the algebraic sum of the currents entering and exiting node V2 must be 0. All right, that's it for that step. Next, we need to rewrite each current in terms of the node voltages and resistances. So here's where we use Ohm's law, and as we covered in the practice, make sure that you subtract in the correct direction when applying Ohm's law. So we'll see that our current I1 is drawn as current flowing from V1 to V2 through the 3 ohm resistor. So we'll see that I1 must be equal to our 10 volts minus V2 divided by 3 ohms. Our I2 current must be equal to V2 divided by 6 ohms. It's basically V2 minus 0 over 6 ohms, but we don't necessarily need to write the minus 0 because it's just subtracting 0. I3 will be equal to our voltage V2 minus 0 volts divided by 12 ohms, or just V2 divided by 12. And then finally, I4 is actually given as 4/3 ampere. So we just take that current source that was given. So therefore, if we substitute these in, we determine that our Kirchhoff's current law equation becomes 10 minus V2 over 3 minus V2 over 6 minus V2 over 12 minus 4/3 equals 0. Our last step here is to simply solve for V2. And we'll see if we multiply all the stuff in our equation by 12. I like to do that to get rid of fractions. If we multiply both sides by 12, we will determine that we will have 40 minus 4v2 minus 2v2 minus v2 and then minus 16 equals 0. So minus 7v2 is equal to negative 24. That means our v2 is 24/7 of a volt, or approximately 3.43 volts. So there you have it. Now we have found the voltage across all of our nodes. So we know V1 is 10 volts, V3 must be 0, and V2 is 3.43 volts. Now that we know those voltages, we can actually go back and solve for the currents if we'd like, and we know everything there is to know about this circuit. Okay, let's continue on to example 3. And example 3, we are being asked to write the equation for each node in terms of node voltages and resistances. And then we want to solve for the voltage of each node. Once again, just to make sure your answer is consistent with mine, we are told to let the bottom node be our ground node. All right, so let's go ahead and start. So our first step, of course, is to identify our nodes. So I'll call my first node here, this will be my node 1. And I'm going to say that that node, let's assume it's sitting at voltage V1. I'm going to call this whole area node 2 with voltage V2. And then I have my node 3 on the right. And I'm going to assume that whole area is sitting at voltage V3. And then, of course, our bottom node here, this is our reference node or ground. All right, so nodes have been identified. Now we need to assume some currents flowing in and out of each node. So let's go ahead and assume some currents. And here it's really helpful to draw arrows because it will help you be consistent. You need to make sure you keep the current directions consistent for the entire circuit. So I'm going to assume that I have current I1 flowing upward. I'm going to assume current I3 flowing to the right, I2 flowing through to the right through the 2 ohm resistor, and then I will have I4 flowing upward. Notice I3 is still flowing into node 3. I'm going to assume I have I5 flowing through that 6 ohm resistor, and then I'm going to assume a current I6 flowing downward through my 8 ohm resistor. I have no idea whether these current directions are correct. Some of them could actually be going the opposite way, but remember, it doesn't matter what direction we assume as long as we are consistent with our currents when applying Kirchhoff's current law. So please make sure you just pick a direction and stay consistent as we demonstrate here. All right, so now that we have assumed currents, let's go one by one and let's apply Kirchhoff's current law to each node. Let's start with node 1. You'll see that node 1 has I1 entering and I2 and I3 are leaving. So Kirchhoff's current law will give plus I1 minus I2 minus I3 equals 0. So next, Kirchhoff's current law on node 2 you'll see we have I2 entering, I4 entering, and I5 leaving. So we will have plus I2 plus I4 minus I5 equals 0. And then next we have node 3. For node 3, we get, in this case, we have I3 entering, I5 entering, and I6 leaving. So in this case, for node 3, we get plus I3 plus I5 minus I6 equals 0. Now that we have our Kirchhoff's current law equations, it's now time to rewrite each current in terms of the node voltages and the resistances. So in this case, by applying Ohm's law and using the information given, we get the following. We know that I1 is just 2 amps because that was given to us. I2, paying attention to direction of our current, we can say that I2 must be equal to V1 minus V2 divided by 2 ohms, since we assumed flow from V1 to V2. And our current I3 will be given by V1 minus V3 divided by 4 ohms. Once again, paying attention to the direction we're flowing. And then finally, I4, we know is 3 amperes. That's given to us. And I5, in this case, is equal to V2 minus V3 divided by 6 ohms. And then finally, last but not least, I6 is equal to, in this case, V3 minus 0 divided by 8, or just V3 over 8 ohms. So we just need to substitute these values back into our Kirchhoff's current law equations. And if we do that, we will get a system of 3 equations and 3 unknowns. So I encourage you, go ahead and do this substitution, and I'll write on the next slide what we get. All right, so if you have performed the substitution correctly, you would get a system of 3 equations and 3 unknowns like shown here. And the next step would be to use a system of equation solver, or whatever equation solving method of your choice. And if you do that, you should end up with 51.33 volts for V1, 53 volts for V2, and 40 volts for V3. And here's a quick example. My preferred solver is Wolfram Alpha. So if you go to wolframalpha.com, type in solve system of 3 equations, you can see that you can actually just type those equations directly in, and that's how you can come up with the result. Just be careful, make sure you type everybody correctly, including using parentheses as needed in order to preserve subtraction. But that's it for example 3. All right, example 4 asks us to find the voltage at each node of this circuit. And just so that your answers are consistent with mine, I ask that you assume the bottommost node is your reference node. So we assign ground to our bottom node. So let's go ahead and give this one a try. So upon first glance, you'll see that this circuit actually has a couple special cases in it. Notice we have the 10-volt source that will be between our ground and the topmost node. And then we also have a 5-volt source between 2 nodes. So we want to make sure that we consider those. Let's go ahead and identify our nodes first. Let's go ahead and take this whole topmost area to be node 1. And we could call this voltage V1, but notice that node 1 is between our 10-volt source and the ground. So node 1 has to be sitting at 10 volts. And then next, we have our node over here in the middle left. Let's call this node 2. And let's assume it has voltage V2. We don't know what voltage that is yet. We're just going to call it V2 for now. To the right of our 5-volt source, we have another node. I'll call it node 3. And let's assume this guy is sitting at V3 volts. And finally, our last node is our node that we've assigned the ground. So once again, we do have some special cases here. We know that due to the 10-volt source between node 1 and the ground, we know that our node 1 must be 10 volts. And then our other special case is the 5-volt source between V2 and V3. You'll remember that if we have a voltage source between two nodes, we need to designate what's called a supernode. So we can treat this whole section, V2, V3, and our 5-volt source, as a supernode. And you'll remember when you have a supernode, you need to apply Kirchhoff's current law to the supernode. And then you can also get an extra equation from the supernode itself. In this case, it will relate V2 and V3. So let's go ahead and first apply Kirchhoff's current law to our supernode. And in order to do that, we need to assume some currents. And again, you don't have to guess correctly, you just need to assume a current direction. So I'm going to go ahead and number my currents like this. I will have I1 and I2 flowing downward from my 10-volt source, and then I will have I3 and I4 flowing through the 68 and 150 ohm resistors. Now that we have those currents, we can apply Kirchhoff's current law to the supernode. We have I1 and I2 entering, so those get positive signs. And I3 and I4 are leaving, so those get negative signs. And there's our equation. Our next step is to rewrite this supernode Kirchhoff's current law equation in terms of our voltages. So that's in terms of our voltages V2 and V3 and our resistances. Once again, you'll want to be careful here to make sure you subtract in the correct directions. We note that our current I1 must be equal to 10 volts minus V2 divided by 10 ohms, because in this case we're flowing from that 10 volt node 1 down to V2 and passing through our 10 ohm resistor. Just once again, Ohm's law. Similarly, I2 must be 10 minus V3 divided by 47. And by the same reasoning, we'll see that I3 will be our voltage V2 minus 0 divided by 68, or just V2 over 68. And I4, similarly, will end up being V3 over 150. So be careful there. Make sure you subtract in the correct direction. That's a common mistake for these types of questions, is to accidentally subtract in the wrong way based on the arrows you drew, and that would create a sign error. And if you substitute all of these into the Kirchhoff's current law, we will end up getting our node equation for the supernode. We will end up with 10 minus V2 over 10 plus 10 minus V3 over 47 minus V2 over 68 minus V3 over 150. All that must be 0. But notice we still need one more equation relating V2 and V3. But you'll remember there is one more equation that we can get. The thing to remember is that the supernode itself gives us a second equation. As we drew, we know we have our node V2, our 5-volt source, and then our node voltage V3. So we can say that V2 is sitting 5 volts higher than V3. Therefore, V2 minus 5 volts equals V3. This is the second equation that we need in order to solve for our voltage V2 and V3. And so if we go ahead and do that, if we take our two equations and plug them into Wolfram alpha, we will actually determine that we will have V2 is approximately 9.481 volts and V3 is approximately 4.481 volts. So that's for V2 and V3. And so once again, you can see that by using the supernodes and the step-by-step node analysis process, this somewhat ugly-looking circuit was actually not too nasty to solve for. All right, let's move on to our next example 5. In this example, we're being asked to determine Ix and the amount of power supplied by the dependent current source. And so the first thing you want to be careful here is to notice that this 20-volt source is not in parallel with the dependent source. Because notice this 200 ohm resistor is also sitting here. And in order for these two components to be in parallel with each other, they must experience the same voltage drop. Because this 200 ohm resistor is here, the 20-volt source and the 9Ix dependent source cannot experience the same voltage. Some voltage must be spent across the 200 ohm resistor. So be careful there. Common mistake is to accidentally forget about this 200 ohm resistor, and you would end up with an incorrect result. So this question is a good example of a question that can be solved using different parts of our node analysis procedure. The first part of the question asks us to find Ix. And we can actually do this by using Kirchhoff's current law. And specifically, Kirchhoff's current law at the top node. You can see that we have 9Ix entering from the bottom. We have Ix entering from the right. And we have 2 milliamps exiting toward the left. So if we apply Kirchhoff's current law, we can say that minus 2 milliamps plus 9Ix plus Ix must be 0. So therefore, if we go ahead and solve for Ix, we'll determine that 10Ix is 2 milliamps. So Ix must be 0.2 milliamps. So we've determined the first part of our question. That is done. Next is to find the power supplied by our dependent current source. Well, we know that power is given by current times voltage. We know that we have a current of 9Ix, so that's easy to find. But this voltage, the voltage of our 9Ix source, can be found using node analysis, or by using a node equation. That's not the only way to find the voltage here. You could have chosen to use Kirchhoff's voltage law or other techniques, but we'll go ahead and just illustrate how a node equation could be helpful to find this voltage. Because once we know the voltage of that 9Ix source, then we can plug it in to get our power supplied. So in this case, let's go ahead and apply Kirchhoff's current law to our top node. So here, we can assume we've got 2 milliamps leaving. We have 9Ix entering, and we also have Ix entering. And we can also write our voltage in terms of V source. We can say that Ix is 20 minus V source over 200. So we'll use that as well. So essentially what we get is we will get the following equation. We have plus Ix minus 2 milliamps plus 9Ix equals 0. But Ix in terms of our unknown voltage will be 20 minus V over 200. And then we can plug in 2 milliamps. And then 9Ix, that will be plus 1.8 milliamps, because Ix is 0.2. And we can determine in this case that 20 minus V over 200 must equal 0.2 milliamps. And so if we go ahead and solve this for our voltage, we'll determine that our V is actually going to be 19.96 volts. And then we can do power. Power is current times voltage. So in this case, we get 9Ix times 19.96 volts. And we will end up, in this case, with about 35.93 milliwatts of power. So example 6 is similar to an old exam question which I had given in the past. In this question, we're trying to find the voltage across the 8 ohm resistor. Let's give this a try. So you'll notice, hopefully right away, that we actually have a supernode in this question. And so let's go ahead and do node analysis with a supernode. And in this case, we have some nodes next to our supernode. We have, let's call it our voltage V1 on the left of our supernode and our voltage V2 on the right of our supernode. And in this case, it's also important to notice if we let our bottom node be ground, then the voltage we're trying to find, voltage across the 8 ohm resistor, is equal to our V2 value. And we can also notice that based on that supernode equation, the way our supernode is written, we know that our voltage V2 is sitting 3IA higher than V1. So we can also say that V1 plus 3IA equals V2. All right, so let's go ahead and do our node analysis. Specifically, we will apply Kirchhoff's current law to this supernode. And to do that, we'll want to assume some currents. So I'm going to go ahead and assume I1, I2, and I3. Let's have I1 enter our supernode from below. I'll assume I2 is flowing downward, and then finally this I3, we'll just call it I sub A since that was already given to us. We have I sub A flowing downward. Then if we apply Kirchhoff's current law at the supernode, we will get plus I1 minus I2 minus IA equals 0. Our next step is to rewrite the supernode equation in terms of the node voltages. And if we do this, we determine that I1 is 6 amps. I2 will be given by V1 minus 0 over 4. And then finally, we have our I sub A, which is given by, in this case, V2 minus 0 over 8. So therefore, our supernode equation becomes 6 minus V1 over 4 minus V2 over 8 equals 0. We need the second equation for V1 and V2 in order to solve. And notice we have this V1 plus 3 I sub A. So notice this equation also allowed us to relate the IA that our dependent source depends on to our node voltages. You'll remember that was one of the things we needed to do when we had a dependent source in our node analysis. All right, so now that we have this, we have one equation here, and we have our second equation here. We've got two equations to unknowns. Remember, we know I sub A can be written as V2 minus 0 over 8, so that can also be plugged in. And this will allow us to solve for our final result. And so in this case, we'll determine that V2 is equal to V1 plus 3/8 V2, just by substituting into there. And therefore, we'll see that V1 must be equal to 5/8 times V2. We can take this and substitute back in to our equation 1. And if we do that, multiply both sides by 8, we can see that we'll get 48 minus 2 times 5/8 V2 minus V2 equals 0. This gives us 48 minus 2.25 V2 equals 0, or V2 is 48 divided by 2 1/4, or 21.33 volts. As we mentioned before, V2 is actually equal to the voltage we want to find, so that means that the voltage across our 8 ohm resistor is 21.33 volts. And there you have it. That is one way to solve for this circuit using our node analysis. All right, let's go ahead and finish up with our last example. In this last example, we want to find our voltage across the 6 ohm resistor. This question is actually pretty similar to one I asked during an exam, and you'll see it's actually pretty straightforward once you have it set up properly. The key thing that you want to notice here is the 8 ohm and 4 ohm resistors. The 8 ohm and 4 ohm resistors are in series with each other. Both of these must experience the same current because there is only one path for the current to flow. So what that means is since the two resistors are in series, they can be combined and simplified. That also allows us to connect this ground node and have it at the bottom of our circuit. And so in this case, we can redraw the circuit as the one below. So notice, because the 8 ohm and 4 ohm resistors were in series, we could combine them into a single 12 ohm resistor. And in this case, we still have our dependent sources current I sub x flowing through there. So now that we have our simplified circuit, we can go ahead and do some node analysis. Let's go ahead and make this bottom node our ground. You'll notice that the node up here in the top left, that guy's just sitting at 12 volts because of the 12 volt source. And then this node over here, the voltage there will be the voltage we're trying to find. So let's do node analysis on this top right node. And to do that, we first need to assume some currents. So let's go ahead, we assume current I1 entering from the left. We have I2 coming upwards, and I'll assume current I3 flowing down. Kirchhoff's current law will give us plus I1 plus I2 minus I3 equals 0. If we substitute in and rewrite in terms of our node voltages, we will determine that we have our I1 is given by 12 volts minus V6 ohms divided by 12 ohms. Then we have 2Ix current entering from below for I2. And then finally, we have our minus V6 ohms divided by 6 as our third term. And all of that must sum to 0. And you'll notice, well, wait a minute, we have this Ix here. How do we relate I sub x to the rest of our circuit? And how do we relate Ix to V6 ohms? And in this case, the important thing to recognize is we have I sub x entering from the left. We have 2Ix from the top. So we actually have 3Ix current flowing through our 6 ohm resistor. So since we have 3Ix current flows through our 6 ohm resistor, we can say that V6 ohms is also equal to 6 ohms times 3Ix by Ohm's law. So therefore, the voltage across our 6 ohm resistor must be equal to 18Ix. Or we can say Ix is V6 ohms divided by 18. So you needed to do a little clever Kirchhoff's current law here in order to recognize that. But once you have that bit of information, you can substitute it back in and solve. So let's go ahead and do that. Here's what we end up with. So if we plug in Ix equals V6 ohms over 18, and we have the equation 12 minus V6 ohms. So if we solve these two, we will end up with the following. And so again, all that's left is to solve for V6 ohms. And I personally like to multiply everybody by 108, and then that way we get rid of the fraction. After solving for V6 ohms, we end up with 7.2 volts as our final answer. And there you have it. So this was a slightly more challenging node analysis problem, but you'll see that by following the procedures we covered in this sandbox, we were able to get the correct answer. Well, thanks everybody for watching the sandbox and trying these problems along with me. I really hope you found this helpful, and feel free to reach out if you have any other questions on this. And once again, please do take the time to practice this node analysis, and you'll find the more you practice it, the easier it becomes. Feel free to also check out our Lecture 4 for additional information and examples on node analysis. Thanks everyone, and we'll see you in the next video.